Have you ever wondered how industrial motors change direction instantly? Or how electric trains switch from acceleration to braking without delay? What is regenerative braking? What is called 4 quadrant operation? I will answer all these questions in this video. Just stick around till the end of the video. Let's go. We can get answers for all these questions when we know about single phase dual converter. Yes, our topic is single phase dual converter. First of all, let's talk about the quadrants. In electric drives, a quadrant represents the mode of operation based on the relationship between voltage and the current. It gives us idea about how motor behaves under different conditions. In the first quadrant, both voltage and current are positive, that means forward rotation. In the fourth quadrant, voltage is negative and the current is positive, that means forward regenerative braking. In the third quadrant, both voltage and current are negative, that means reverse rotation. In the second quadrant, voltage is positive and the current is negative, that means reverse regenerative braking. Before we dive into our topic, now let's discuss about some characteristics of full wave controlled converter with RL load. Let's talk about the two modes of operation of full wave controlled converter with the RL load. We all know about the working of the full wave controlled converter, right? This is the circuit diagram. The positive half cycle is represented in the rose line and the negative half cycle is represented in the orange line. We all know about the average output voltage equation. V average equal to 2 Vm by pi cos alpha. This is the output waveform. We can say that the output voltage depends upon the firing angle alpha. When the firing angle alpha is less than 90 degree, our output voltage is positive. When the firing angle is greater than 90 degree, our output voltage is negative. Based on that, we are classified into the two modes. In mode 1, alpha is less than 90 degree. Mode 1 is called as conversion. And in mode 2, alpha is greater than 90 degree. Mode 2 is called as inversion. In mode 1, when firing angle is less than 90 degree, our output voltage is purely the positive DC voltage with some negative spikes due to the current flow from inductor to the source. In mode 2, when the firing angle alpha is greater than 90 degree, the current flow is from load to source. That is, voltage is negative and the current is in the same direction, so the current is positive. This process is called inversion. That is, DC is converted to AC. Due to the inversion process, we can do regenerative braking. So we can say that the full wave controlled converter with RL load works in both first and fourth quadrant. That is, forward rotation. It can do forward rotation and forward regenerative braking. Let's come back to our topic, single phase dual converter. A single phase dual converter consists of two full wave controlled converters connected anti-parallelly to provide bidirectional current flow. This single phase dual converter is classified into two modes, circulating current mode and non-circulating current mode. Now, what is circulating current? Circulating current refers to the current which is flowing throughout the circuit without flowing through the load. To reduce the circulating current, we will use two reactors to reduce the circulating current flow throughout the circuit in circulating current mode. In non-circulating current mode, we will not use any reactors. The converter 1 acts like a typical full wave controlled converter with a RL load. If we give triggering pulse less than 90 degree, the converter 1 will act like a converter. And if we give triggering pulse greater than 90 degree, the converter 1 will do inversion. The story is entirely different for converter 2. Since the converter 2 is connected anti-parallelly, if we give triggering pulse less than 90 degree, converter 2 will do inversion. If the triggering pulse is greater than 90 degree, converter 2 will do conversion. We know that the average output voltage of a full wave controlled converter with RL load is 2 Vm by pi cos alpha. The overall output voltage is equal to the V output 1 and which is equal to minus of V output 2 since it is connected anti-parallelly. We can do a simple calculation. V2 Vm by pi cos alpha equal to minus 2 Vm by pi cos alpha. By doing the calculation, V output 1 equal to minus V output 2, we get the relationship between alpha 1 and alpha 2. that is alpha 1 plus alpha 2 equal to 180 degree. The summation of the firing angles of the converter 1 and the converter 2 is equal to 180 degree. This is the basic condition for the operation of a single phase dual converter. Now let's talk about the characteristics of circulating current mode. In circulating current mode, we all know that both converters will work simultaneously. Take a look at this waveform. If we give alpha firing angle to the converter 1, it will do conversion and the output waveform of the converter 1 will look like this. If we give firing angle at pi minus alpha to the converter 2, it will do inversion and the output waveform of the converter 2 will look like this.
Now the conditions for the 4 modes of operation in circulating current mode is tabulated here.
Now let's talk about the non-circulating current mode characteristics. We all know that in non-circulating current mode, only one converter will operate at a time. Take a look at this waveform. If converter 1 do conversion, the output waveform will look like this. If the converter 2 do inversion, the output waveform will look like this.
Now the conditions for the 4 modes of operation in non-circulating current mode is tabulated here.
We can see about advantages and disadvantages for both circulating current mode and non-circulating current mode. First, circulating current mode advantages: fast response due to continuous operation, smooth transition between forward and reverse operation, suitable for application requiring higher dynamic performance. Disadvantages: requires an inductor to limit circulating current, increase power loss due to continuous conduction, higher harmonic and poor power factor. Next, non-circulating current mode advantages: higher efficiency as no circulating losses, simpler control and circuit design, lower harmonic and better power factor. Disadvantages: slower response due to switching delay, not suitable for high speed application requiring smooth transition, requires precision synchronization.
Hello everyone, today I'll explain the applications of single-phase dual converters based on their 2 modes, non-circulating current mode and circulating current mode. These converters enable bidirectional power flow, making them essential in various industries. Non-circulating current mode applications. In this mode, only one rectifier operates at a time, avoiding energy loss but requiring a delay for safe switching. It is used in DC motor drives for smooth speed control in CNC machines, robotics and textile industries. Batteries charging and discharging in EV chargers that allow both charging and discharging. Industrial heating systems for precise power control in induction and resistance heating. Circulating current mode applications. Here, both rectifiers conduct simultaneously, enabling quick switching. It is used in regenerative braking systems found in elevators, cranes and metro trains, allowing energy recovery. UPS and energy storage, ensuring instant power transfer and backup power systems. High frequency power supplies used in research labs and industrial power control. To summarize, non-circulating mode is energy efficient while circulating mode is ideal for fast response applications. Both are vital for modern power control systems. Thank you.
Thank you for watching this video and keep exploring.